I'd like to welcome you to this first lecture on Euclid Elements. In this video, we will go through all the definitions, the postulates, and the common notions, so that we are fully prepared to tackle the content of the upcoming lectures. Now, I do realize that some stuff in this video may come across to you as being blatantly obvious. However, I do encourage you to stay with it, as this represents the fundamental truth on which Euclid based his work. Should one of the notions in this video fail, then the validity of the entire book can be brought into question. We set off on our journey with the definition of a point. And Euclid defines a point as something of which there is no part, and therefore a point is just a location in space and should not be confused with something that has a volume or a mass. The notation of a point is a dot, which is infinitely larger than the point itself. And a letter is often added next to it to aid in the explanation process of proofs. Oliver Byrne, who is the author of the popular edition from 1847, explains the essence of a mathematical point with a visual aid. If three colors cover a portion of the screen, the place where they meet is neither red nor blue nor yellow. It occupies no portion of the plane, otherwise it would belong to one of these colors. But it does exist, so it has a position, but not a magnitude. Now, one can imagine a line as an infinite amount of these dots placed next to each other. Euclid defines the line as a length that has no breadth, with points at the extremities or boundaries. And similar to the dot, what we draw on the screen has a breadth which is infinitely larger than the line that we actually want to represent. And this can again be explained with a visual aid. If two colors cover a portion of the screen, where they meet it is neither red nor blue. No portion of this plane is occupied by this junction, so the line cannot have a breadth, it only has a length. Of course, a line can also be a straight line, and Euclid defines the straight line as any line which lies evenly with points on itself. Oliver Byrne defines the straight or right line as that which lies evenly between its extremities, which we know to be points. And similar to the point and the line, Euclid defines a surface as that which has length and breadth only. And as with the straight line, a plane surface is defined as a surface which lies evenly with straight lines on itself. This surface is an example of a figure, defined by Euclid as that which is contained by some boundary or multiple boundaries. And later editions define a figure as being enclosed on all its sides by at least one line. Now, after this, Euclid goes on to define the plane angle as the inclination of two lines that meet one another in a plane and are not lying in a straight line. And when these lines containing the angle are straight, the angle is called rectilinear. And when one straight line standing upon another straight line makes the adjacent angles equal, each of the angles is said to be a right angle, and each of these lines is said to be perpendicular to the other. Euclid also defines the obtuse angle as being greater than a right angle and an acute angle as being less than a right angle. Now let us move on to the circle. A circle is defined as a plane figure bounded by a single continued line called the circumference, having a unique point contained within it, from which all straight lines radiating towards the circumference are equal. And this unique point from which all equal lines are drawn is called the center of the circle. The diameter of the circle is defined as a straight line traveling through the center, terminated in each direction by the circumference. Then, the figure contained by the diameter and the part of the circle cut off by it is called the semicircle. A rectilinear figure is that which is contained by straight lines, and within these, trilateral figures are those contained by three straight lines, quadrilateral figures by four straight lines, and multilateral figures by more than four straight lines. So here we think about pentagon, hexagon, heptagon, etc. A triangle whose sides are all equal is called an equilateral triangle. And a triangle having only two sides equal is called an isosceles triangle. A scalene triangle is one which has no equal sides. And a right angle triangle is one which contains one right angle. An obtuse angle triangle is one which contains one obtuse angle, and finally, an acute angle triangle is one which contains three acute angles. And of the four-sided figures, we can say that a square is that which has all sides equal to one another and contains four right angles. A rectangle is that which is right-angled but not equilateral. And a rhombus is that which is equilateral but not right-angled. And finally, a rhomboid is that having opposite sides and angles equal to one another, but it is neither right-angled nor equilateral. Any other quadrilateral figures are called trapezia. And lastly, we can say that parallel lines are straight lines which, being in the same plane and produced to infinity, will never meet one another. Now let us move on to the postulates. Now, a postulate is essentially a problem, the solution of which is assumed by us and serves as a basis for our geometric reasoning. Now, we start off by postulating that a straight line may be drawn from any point to any point, and this line may be extended however far we want. The third one is that we may construct a circle with any center and with any radius. Now, the fourth one is that all right angles are equal to one another. And lastly, we have the most controversial postulate, so I ask you to brace yourself. It states that a straight line falling across two other straight lines with an internal angle whose sum is less than two right angles, then these two straight lines, if we produce them to infinity, will meet on that side once and will not meet on the other side. Now, you might be forgiven to think that this last postulate does not belong here, right? It's weird. However, there have been many attempts to prove Euclid wrong in this regard, and it turns out that this postulate absolutely should be here, and it effectively specifies that we are dealing with the geometry of a flat space rather than a curved space. Now, to conclude with, we will mention the common notions, and a common notion or axiom can be regarded as a theorem, the truth of which is granted without a demonstration. So let us begin by saying that things equal to the same thing are also equal to one another. And consequently, if equal things are added up to equal things, then the whole is equal, and if equal things are subtracted from equal things, then we can say that the remainders are equal. And we also have that if we have a whole, then it is greater than a part. Now, Euclid also says here that things coinciding with one another are equal to one another. At first glance, it seems that Euclid simply says that two identical things are equal, or more generally, that anything equals itself. But it is of course questionable how useful this statement is. So traditionally, this is interpreted as a justification for some use of a principle of superposition. Using this principle, we can say that one thing can be moved to coincide with some other thing, and then we can say that they are equal. Now, Euclid rarely uses this method, and it has been criticized as one of the weaker aspects of his geometry. Because how does one actually move stuff on something else, right? Nowadays, any geometric thing would be subjected to an isometric transformation in order to achieve superposition. But such a thing is of course not mentioned in Euclid's text. Now, this common notion will be used in one of the earlier propositions in the text, so we will return to this discussion at that time. I have now told you everything that we need to know to progress to the propositions, which is the exciting stuff. Thank you for watching this video, and I will see you in the next one.